Okay, we're okay, we're okay. All right. So I think I was talking about this a little bit. You are here. I have the example solution for diff that I worked on this weekend. I had fun writing it, but it was a lot of strings in Rust, and I kind of hated that. Diff and patch are the same thing, and we can look at a quick example here. So, can we look at a quick example here? All right. So, this is the Fibonacci code I wrote last time for the dynamic programming thing. I'm just going to motivate diff right now, and then we'll get into class. Okay, so I intentionally left it in what I'm going to call a degenerate state, and the degenerate state is it has commented out code. Really, that's not the way you're supposed to do things. And this is inside a Git version control system. So I think there's a proper way to handle this that I'm going to show you, and then we're going to experiment with it a little bit. So one thing I could do is I could change which branch I'm on. So I think I can say to git checkout B, and then I'll have a branch called like print. Is that right? Okay, and so then when I say git status, I'm on branch print. I have no changes to be committed. And then I'm going to set this so that it is printing. There we go. Okay. And so then I will git commit. I'm going to commit my changes. Prints are not commented out. Okay. And so that's one way to do this. And then separately, I might want to have a version that doesn't have prints. So I will git checkout. B means branch. And we'll have non-print. Okay? Now, circ main is still currently the same. But I can go ahead and edit this over to the way I wanted it to be. So I'm going to take out the prints. And in this case, at these lines, which is 5 through 8, or 5 through 7 now, it makes sense to actually remove entire lines. So here we do. Is that right? Okay. And then down here, we just remove this line. Okay. And so I'm going to git commit, removed print statements. Okay. So I can cargo run. What are the arguments to this? Let's see. Cargo run 10f. Okay? Is that how it's supposed to work? Oh yeah, it just doesn't print anything at all, right? And then if I put in like really big numbers here, something explodes. I don't really remember how this code works. Okay. And then if I change back to git checkout print, and then I cargo run 10f, do I get prints now? No, nothing's printing. Cat circ main. Oh no, my prints are gone. Maybe I don't know how git works. Does anyone know how git works? Okay, that's fine. So I'm going to make a copy of this. Call it other.rs. I'm going to mvim other.rs. I'm going to add the print statements back in. You're going to have to play around with this too. The reason it's being taught this way is because I'm learning it at the same time. This is slow. Close the expression. Okay, and then this is fast. Okay. Then if I do diff circ main circ other, right, I can get the following diff. So the problem with diff, it means difference. but diff is a command that refers to the diff command. And the thing that the diff command creates is also called a diff. So this is, I'm showing you a diff that I made with diff. This is not great. There's no graceful way to describe it, but this is a way to see the differences between two files. This is either going to be the lab or the homework. I haven't decided yet. Now, something to look at. This is not JSON, but obviously should be. What do I mean obviously should be? So these are two file changes. So these things should be at the same sort of abstraction level. So my line of thinking is, this is the value to a key. What is the key? The key is left, which is sork main. The key over here is right, which is sork other. So this is the value of line 5 in sork main. So that should be a hierarchical relationship that you would preserve with JSON. And this should be the value of lines 5 through 8 in sork other. And that's the difference. So if I change sork main to sork other, I should look up this value by key, and then I should change it to this value by key. And I should do the same thing here. This does not exist in sork main, so it is an add, A for add, C for change. And we change line 15 of sork main to line 19 of sork other in order to get sork main to turn into sork other. Okay. Now, I can take this and I can store it as a diff file, which I'm going to call, of course, diff.diff, because the name of the file is diff and the type of the file is diff. And then somehow I can patch options, original file, patch file. Okay. Okay, so I have head source main, and currently it doesn't have the print statements in it, but I can patch with the diff I created sork main. Why is that not finishing? Does that not work? How does patch work? No, I know how contraception works. Unix. Give me an example. Old file, new file, patch file. Okay. I don't know why that worked. And now that has successfully added the prints. Okay? And I think I can undo this with reverse. Okay. Now, for those of you that want to keep track of versions of software, which is obviously all of you because you took this class voluntarily, and none of you are here under duress, it should be clear what the usefulness of diff and patch is. Okay. Now, let's do one other thing real quick, which is you are working on longest common subsequence, right? Okay. So let's make two quick files. We'll make vin and cal. IESEL. Why am I putting these online? Diff is comparing lines, that's not comparing text. Cal.text. Oops. Okay. So I can diff vin and cal. And this will show you the negation of the longest common subsequence. This is only the differences. So the letters that are present here are exactly missing vin de, right? So once you have implemented longest common subsequence, in order to implement diff, you change it to work on lines instead of characters, and then output the differences instead of the similarities. So you sort of have already solved this algorithmic problem, but you have to apply it to an actual existing problem. So anyways, that's going to be the homework this weekend somehow. I'm going to decide how to actually assign it tomorrow. And then that's going to be the basis of the version control system once we get to that. Now, where does hashing come into this? I'm glad you asked. We do 512 sum. You can hash these diffs, and then you can be confident they haven't been tampered with, right? And if you have more than one diff, for example, if you also have, remember diff.diff? Oh, it's in something. Fib. There you go. You can also hash that. And then maybe you need to hash both of those things together to make sure no one's messing with it. No problem. Am I smart enough to do this? Let's cat fib diff.diff and diff vin.text cal.text. Okay, so if we cat those together, okay, that's both of the diff files. And we can pipe them into 512 sum. Or SHA-512 sum. We can pipe the hashes together. I have no idea if any of this will work. We were close. Oh, wait, no, that's just typo. You can take the hash of the hashes. And when you start taking one hash of two hashes, that should start to look a lot like a tree. And that's what we're going to work on today. So the two things going on in parallel is the underlying technology that is going to allow us to manage versions of source code. And then separately from that, we're going to work on providing assurances that no one tampered with the source code. We're going to do those at the same time. And the reason we have to do them at the same time is like, how else would you do it, I guess, right? Like, maybe we don't have to do it at the same time. Okay, Merkle. Separately from all of that, so this class is like motivated by the running example, but there's also like one other pretty good reason to cover this stuff, which is that whoever selected the motivating example, which is me, tried to select an example that would touch on a lot of the relevant topics in computer science and then still have you put them together. And so Merkle tree is a great way to teach trees. The same way dynamic programming was a good way to teach multiple dimensional arrays. The same way stacks and heaps are good ways to teach stacks and heaps and so on, right? So my nervousness historically has been when I come into a classroom and say like, hey, we're going to learn an abstract data type that everyone instantly falls asleep and is incapable of learning everything because it seems so irrelevant. It is in fact true you don't have to implement your own B-tree map in Rust. It already exists, right? It is not the case that you will never have to know what a Merkle tree is in your life. That's crazy. Everyone needs to know what Merkle trees are all the time because they're everywhere. So we're going to learn about trees, heaps, and Merkle trees. Okay, trees. This is just a little bit of a blast from the past on the sort of the graph theory discussion, right? A tree is a type of graph. A graph is an ordered pair of nodes or vertices and edges. The edges may or may not be ordered. We kind of don't care. Some of you know what a linked list is. Do you all know what a linked list is? I've asked this before. Okay. What's the difference between a linked list and an array list? Okay.
An array list is sequential in memory, and a linked list isn't.
Okay.
And also, just works different.
So they're similar, but they're different.
Mm-hmm.
Okay, that makes sense to me. Which one is easier to insert something in the middle?
Array.
Yeah, it's definitely linked list.
Oh.
You're cooked. Yeah, thank you for trying. And why is that? Because I have to move big blocks of memory to put something in the middle of an array. I'm going to draw something on the board because why not, right? I'm going to give a linked list of my favorite classes I'm teaching this term. And this is the order they occur during the day, not the order of favoritism. Am I even willing to do this? I'm going to list my 5 favorite integers mod 6. You got the 1? Oh, gosh. Okay, you got 1. That's a 1. That's not an A. If I put that in a computer vision framework, it would not be able to conclude it's a 1, right? You got the 2, right? Oh, now I have to decide how to draw this. I'm going to draw a linked list, right? You got the 4. You got the 5. Oh no, I forgot one of my favorite numbers, the 3. Okay, and then here's the competing formulation. 1, 2, 3, 4. Now, I think typically we would think of this as a Rust vector. So this is a vec I32, most likely. What is this thing? I have no idea. It's probably a custom structure, right? And that custom structure probably includes, what are these arrows? So you probably have a data, which is an I32, and then you probably have a next, which is going to be what? Probably an option box. What's this thing called? It's called a struct LL. I guess they have to be capital. Okay. So, to store 4 of these things in an array list, right, it's 4 times 32 bits. What's that? 128. Okay. Also known as that much. Okay. And then, now, we don't know how chunky the option box is, right? But I'm guessing it's quite large, right? Because however big this linked list thing is, it has to store a memory location. I don't know that the box is taking up more or less space, but there's probably some overhead in Rust for that, and then there's probably some overhead for the option as well. I'm guessing this thing costs 128 bits. I've been wrong before. I'm guessing this costs 32 bits. So you're using hella bits on this, right? And what do you get in exchange? Well, when I put 3 in this, all I do is I detach this. You've seen this before. Put in the 3. Bam. And can I do that in Rust? Absolutely not. Like, the ownership model will explode. Everyone will be screaming. Like, Rust C is going to take like 15 minutes to compile or something, right? But nominally, if you were using a programming language that made sense, you can do this, right? Now, in order to put, I messed up my example. That's 4 and 5. Okay, now to put 3 in the middle of this, what do I have to do? And you're like, that's not that bad. All I have to do is put another box here and then copy things down, right? 3, 4, 5, or over or up or whatever. Copy things in that direction, right? Like, I high-key cheated a lot there because I just assumed that if you have 128 contiguous bits, you can just find more bits at the end of it. You cannot assume that, right? What if the thing that is right here is your private key? Like, that would be bad, right? What if the thing right here is your embarrassing secret, right? Or like maybe the operating system's living there. I mean, it's not, right? But you can't assume that. So, in general, if you want to add things in the middle, you use the little linked list because it has linear time insertion, right? Just because you scan. Okay, and then some geniuses came along, right? Absolute geniuses, right? And they're like, well, why don't we put the option box LLs inside an array? And then you get the best of both worlds, right? So, anyways, that's how this ended ultimately. But anyways, okay. So I got a linked list. The linked list solves the problem of I'm inserting things in the middle of my list all the time, right? And it also solves the problem of Bitcoin. Okay. Where they never insert things in the middle, but they don't have things in contiguous memory. Okay. So a systems level linked list is a one-array tree. It probably has a data and it probably has some boxes in it, right? How do we feel about sum and box being capitalized? Do we like that? I can't really decide. I don't know. Anyway, like it is, right? So, some of you know that I am a little coffee appreciator, right? And so the decision tree of what type of little coffee to order is a 2-array tree because it is a series of Boolean values. Now, I recently went to a coffee shop. I did not know these existed. It had 3 sizes. They had European, American, and Starbucks are the 3 sizes, right? And so that's 8, 12, and 16 ounces. And then some of them have the double Starbucks, the 20 ounce, right? I just took my CC class down to Ike and they had 20 ounce coffees, and like these students were like, what is wrong with this place, right? And I was like, Seattle did that to us, right? Like Portland was keeping it real, right? Okay, that's not true. Portland was keeping it kind of weird, right? So anyways, you might have an n-array tree if you go to a coffee shop that has been impacted by Seattle, right? Some of you are from Seattle. You don't have to show yourselves. I'm trying to sense it by reading your facial expressions. Okay. I'm going to be a little careful about what I say about Seattle, but not too careful. Okay, all right. So I love trees, and I also love the abstract data type tree, right? Do not take me saying I love trees out of context. That'll get me in trouble. Okay, so usually in computing we use trees to store stuff. The canonical example is the B tree, which is just the generalized binary tree, which is used in databases. Someday maybe I'll teach a database implementation task. Any of you second years? You might be around while I'm teaching databases, right? So that's sort of slated for after compilers. And a fun thing about this department, right, is we teach people how to use SQL, but we don't teach them how to make SQL, right? So it'd actually be a fun closed circle thing. And so I usually use trees to store stuff. What is one of the things that I store in trees? Well, you can certainly view a diff as a tree, right? That's totally fine. The famous example this year will be the operating system page table, which is a mapping between the numerical memory address and the physical memory address that exists somewhere in the circuitry within your device. That is maintained by the operating system, and we will be tangling with those. Next term, that is a hierarchical n-array tree. This term, we are motivated specifically by source control. And what we really want to store is we want to store differences between versions. Let me show you an example of a difference between versions. This is an example, right? So that's what we were starting with today. Okay. Versus last term, just to put this in context, these diffs that we're storing in our version control system, the thing we would be storing if we were doing Bitcoin instead is transactions. What is the interesting thing about both of these? These are both sort of the minimal change to whatever you're keeping track of. The minimal change to the blockchain is the change in ownership of 1 unit of something. The minimal change to source code is a change of 1 version, right? And we don't necessarily say a change of 1 character or 1 line, because oftentimes we cannot determine the precise timing of these things, so a series of lines appear to all be changed simultaneously. And this is the same way in a Bitcoin blockchain, which updates every 10 minutes, right? Everything appears to happen at the same time. Now, I don't do cybercrime. I've heard everyone switch to stablecoins now. I don't know what a stablecoin is. Don't ask me. But please don't invest in either stablecoin or Bitcoin as a result of this class, okay? Right? The thing you should be investing in right now is your own future by focusing on your studies. Okay. You can quote me on that. That one's fine. Okay. I am really sorry that there's something called LCS, and it stands for both longest common subsequence and longest common substring. I am also really sad that it starts with L, because every time I see L, I assume it's referring to least. So the number of times I'm going to say least common substring and mean longest common subsequence is going to be very high. Don't listen to what I'm saying, listen to what I mean. I'm always referring to the algorithm I made you do on your homework, right? That's why we did it, so we all know what we're talking about, right? Just so you know, I have a mostly complete longest common substring implementation at home that I realized was not what I was supposed to be doing slightly before the assignment came out, okay? So, we can see how close strings are to each other. Many changes to code bases are small changes to 1 character line. What was that? I heard you not believing me? Okay. Boom, boom, exactly. Now, it is true this was a motivated example, but I had to plan far enough ahead that I had a code base change this small, right? So frequently there's going to be small changes. In the case of many of the repositories I maintain, it's a change of one file out of some large number of files, right? So still a small change. We can think of these differences as being in leaves of a tree that is holding the contents of a file. So what we want to do somehow with our version control system is we want to ensure oh, wow, I was sure my voice was going to work today. When we are looking at source code, we care about its integrity a lot because we're going to compile that source code into an executable and we're going to run it on our devices, and we don't want our device to do something other than what we intend, right? So we don't want to be running malicious code and so on. So somehow we want to have some confidence in the changes made to some source code, right? And the way we are going to have confidence in those changes is we're going to throw a ton of hashes at this. We're going to hash the changes themselves, and we're going to put digital signatures. So we're going to use SHA to hash the changes, and then we're going to use the combination of SHA and ED25519, or Edwards. Does anyone know? So I've been saying RSA forever. Has any other person ever heard anyone refer to Edwards curve cryptography? Do they call it ECDSA or DSA or something? If, I don't think anyone around here would know. Maybe Professors Colin Starr and Aaron McNicholas would have taught it once or something, but I don't know. So anyways, I'm just going to keep saying ED25519, even though that's literally 8 syllables, right? That's one of the longest things. Okay. So we use ED25519 with SHA to generate digital signatures. So someone knows that I made the change, and they know that the change that's written down must be the change I claim it is because I hashed it, okay? That's a lot of hashes to hold on to. And somehow we're going to have to keep track of all of these hashes and keep them organized and everything. And so the natural thing to do that is to put them in a hash tree. I'm going to try and use hash tree and Merkle tree interchangeably this term. I had every intention of changing these slides' name to Merkle tree. I had every intention of referring to the Merkle root as something other than the Merkle root, but I can't actually find any terms other than Merkle root that refer to the root of a hash tree. So I'm still kind of calling them Merkle trees. I just always want to be clear with you sort of as students in a class where I have to teach that I try not to refer to things by people's names if I can help it, because that's always sort of weird. Y'all know about the Audubon Society, how it doesn't go by that name anywhere. So you're just you're always in trouble if you're referring to things by people's names, right? So anyways, I don't know anything about who Merkle is or anything like that, and it's not Angela Merkel, in case you're wondering. That's what I thought. But there is this thing called the Merkle root, and it is the root of a hash tree. What is a hash tree? Well, I take a series of commits. These ones are sequenced in some total ordering. I don't think you necessarily need a total ordering, but you need some form of tiebreaker, so we imagine they're ordered chronologically, right? What do? We take the commit and we make somehow some SHA digest of the commit. Now, I am skipping a step there, and that step is non-trivial, which is, what is a commit? Is it a diff? That's fine. I think it can be a diff. It is completely reasonable to regard it as a diff. But maybe you want to store that as something else, and I'm sort of suggesting you want to store that in JSON somehow. But some way you don't just store two different versions, but you store the difference between them somehow, probably using LCS algorithm. Okay. So perhaps we imagine over here, before commit 0, there's some original source code. We make some changes, we hash the diff, we make some changes, we hash the diff, make some changes, we hash the diff, make some changes, and we hash the diff, okay? And then, well, it is all too easy to fiddle with one of these digests somehow to do, especially when you have a proliferation of a large number of hashes. It might be a little bit too easy to make a satisfying difference that's going to have the same collision. It might be a little bit too easy if I'm transmitting this over open wires that a few bits get flipped. So what do? Well, you can't actually have necessarily confidence in these digests, so you hash the digests. And you hash them pairwise up to a Merkle root, and then the only thing that you actually have to share with your friends is exclusively the Merkle root, because everyone else can generate the Merkle root from these commit messages the same way. because we can make the same hash of everything. Okay? So this is sort of the technique we're using. The problem we're trying to solve is we want to trust the changes to some source code, perhaps our operating system. Now, I'm imagining in practice we're going to do something like this. We're going to place our commit in some linear data structure, like a stack or array list or a vec. I have not historically thought of this as anything other than a bit string. In Rust, it is unreasonable to think of things as strings because the string type is sort of fighting against us, right? So somehow we are going to store data that represents the difference between two things. So we're going to take this commit, somehow we're going to put it in some form of Rust object, right? Then we are going to hash that commit and store the results. Now, I think it is easy enough, and I've shown you this before, but to say, hey, can I diff these two files? Okay. Can I hash that? We use a pipe to take the output of that and put it in the input to something. I'm going to do a 256 sum because it's shorter. Easy enough. Okay, but now I'm asking you to do all of that in one executable. One of the ways I am cheating here right now is right here where the output of this thing is being treated as a file and the input to this thing is being treated as a file. And that's a little bit different than what you would do if you were making an end-to-end executable like Git that does all of this stuff at once. So somehow you're going to have to write an executable that goes out, looks at some version of code, looks at some prior commit, so it has some sense of what version of code it's changed from, computes the difference over those two things and stores it in an internal Rust structure, and then also hashes that internal Rust structure. And so if that's anything like what you were working on this term, I don't know why ours doesn't come up first. It's like the only thing I use. So SHA2, when we gave out the SHA2 assignment in SHA 512, if we look at all of this, the version of SHA 512 I asked you to make accepts file input. So you're going to have to somehow change how you use this or use some library or crate or something, because I'm going to be asking you to apply SHA to something you're probably holding internally in program memory. That might be kind of weird, and it's something we're thinking about, and that's like one of the steps that we don't skip when we do an end-to-end integration task. Okay. So now I have this commit that I'm storing in program memory somehow, and I have this hash that I'm storing in program memory somehow. But my hash is not yet part of the hash tree. So what I have to do is I have to hash up my tree somehow and get back to the root or change the root or manipulate the root or update different values, which means I need to be storing a library of hashes somewhere, and I need to be creating some vertical hash structure. And I have to do all of this in order to get to the point of having a Merkle root. So we're going to introduce some tree terms to explain how we're going to set up this process. I've previously introduced a few tree terms such as height, depth, connected, things of this nature. I'm now going to introduce one that kind of sketches me out a little bit because some of these are defined differently in different places, but I need to use them. So we're going to introduce the tree term complete. I do want to show you where I'm linking to here. This is kind of a fun website. Zoom in. So the National Institute of Standards and Technology, NIST, this is one of the organizations. They are affiliated with the United States. I think of a lot of public sector cryptography in the United States as being interplay between the NSA, which sort of wants to break all of the codes, and NIST, which sort of wants there to be standards for codes that are hard to be broken, right? These two organizations both are part of the government, but they have different interests, right? NIST just has this kind of cool thing. It's the Dictionary of Algorithms and Data Structures. I don't know why they maintained that, but they started in 1998, so it is probably older than many of us. And this is a cool thing to look at because it's a public resource, and so I'm citing this as ground truth for how to decide what the term complete means for a tree. A tree at which every level, and they define level, right? So this is nice. So everything's defined, except possibly the deepest is entirely filled. At depth n, the height of the tree, all nodes are as far left as possible. That's a little bit of a crazy thing to say because I think you can only specify leftness in a binary tree, and they don't require this to be a binary tree. But whatever. It is a tree that is fully populated down the levels, and then you shove everything in the last row over to one side. So what's that going to look like? We'll see in a minute. Okay. And then we also have the perfect tree, which is a k-ary or n-ary tree, with all leaf nodes at the same depth. All internal nodes have degree or depth or whatever, k. And why am I showing you this? Well, there's no ground truth for what any of these names are. Did that not work? Perfect tree? See if I can find it. Perfect tree. No. I'm going to find it. Perfect. Here we go. A perfect binary tree. Perfect binary tree. So, to me, it seems like it is unclear how you want to refer to the type of structure you have in a Merkle tree, whether you call it complete or whether you call it binary. I am going with complete because of this citation right here. I regard CLR, which is sort of the foundational textbook for computer science, and many of you probably had CLR for CS 351. Is that true? The algorithms textbook, Introduction to Algorithms? Okay, maybe not, I don't know. I regard ground truth for algorithms sort of just like, because we have to have a consensus on things, the CLRS textbook. This is the only textbook that matters in computer science, in my view. It looks like this. All of us in the department have them floating around. I took 2 different classes out of this textbook. They were the same class because they were out of the same textbook. And so because I have, it is so useful to hold CLRS in high regard, I'm going to use the term complete rather than perfect because that's what's used in CLR, so I want to use this. This is an example of a complete tree, and specifically a complete binary tree. If this were a 3-ary tree, this would not be complete because there'd be an extra potential node over here. How does this work? Well, the bottom row is filled in. This one is still complete under the sort of CLR 90 definition because the bottom row is not filled in, but every node in the bottom row is leftmost as possible. This is also complete, even if we only have a single node in the last row. If all of the previous rows or levels are filled in, and the node in the last row is leftmost, then we still regard this as a complete tree. Is this making sense? Thumbs? Yeah, cool, chill. This one is incomplete because the bottom row nodes are not leftmost. So this is an incomplete tree, even though it has the same number of nodes in its last level because it's not satisfying sort of the last level requirement that things be leftmost. So, in a complete tree, we can always place all leaves in a linear data structure like an array. This spelling probably looks kind of cursed. I am responding to a real problem here, and it's hard to explicitly respond to these real problems because my typing is so degenerate, I make so many typos. There doesn't seem to be a widely agreed upon way whether the tree graph data structure you refer to LEAFS because a leaf is maybe not the same word as like the tree leaf. And so the graph leaf may be a regular plural, even though the tree leaf is an irregular plural. This doesn't seem widely agreed upon, so I did what I had to do. I invented a spelling that no one is supportive of, and I'm using that one to avoid angering any particular sides. So those are the leaves, which you would still pronounce it the same way, right? Try and say that other than by saying leaves. Yeah, you can't do it, right? That's cheating. Okay. Leaves. You can also put the V before the F if you want. So, now, in a complete tree, we can always place all leaves in a linear data structure, like an array or a vector, of course. In a complete binary tree, there will always be roughly the same number of leaf and non-leaf nodes as well. So that's kind of useful. So you might be tempted to use the following implementation. I know everyone in this class is a huge fan of option boxes, right? I think we all learned to love them. Yeah, we were like, this is a good way to do things. This Rust is a good language that makes sense. That's what we were all thinking, right? So anyways, you might be tempted to do this. I think this temptation is much weaker in Rust than it is in other languages. I suspect if I asked you to implement one of these in Python, you would absolutely bang out a class that does this, right? And in fact, you can do that. That is completely reasonable to store a complete tree in this manner. But we had this sort of discussion over here where it's like, wait, how much overhead are we actually paying every time we put a data structures box inside an option? That's sort of a lot of nonsense going on. And at the absolute minimum, that amount of nonsense is going to incur source code organization costs, right? We're going to have to be writing code that actually can unoption things and unbox things and so on. And so how do we tell if we're pointing to a leaf or not, right? Like, do you just put a none there? Or like, I don't know. So we're going to introduce a competing formulation, and we're going to motivate it with one of the abstract data structures, which is the heap. The heap is an abstract data structure. Did you all learn about heaps and data structures? Were they called priority queues? Okay. One person nodded, one person shook their head, and the rest of you looked at me like you'd never heard words before. I'm going to say some things that aren't words to establish a baseline. Refrigerator. Oh, see, okay, so some of you recognize refrigerator. Okay, all right. Now I'm going to say a mix of proper and improper nouns, and we're going to see if we can detect them, right? And there's only one proper noun I can ever think of, Sabrina Carpenter. Okay. Q. Oh, no, that's also a proper noun in the Bond universe. Suffix tree. Sorry, what?
Star Trek.
Star Trek? Oh, yeah, there's the data. Oh, no, okay. Never mind. It turns out I can't think of any nouns that are not also proper nouns. Ice cream. Hash table. Okay, so I'm not getting anything, and that's good. You should all play poker. Okay. Actually, wait, should we all learn to count cards and then, like, go to Vegas? It's not that far from us.
It's pretty far.
Yeah, but we're closer than the MIT people.
Mm-hmm.
And they might think they're smarter than us, but we probably seem a lot more normal and are less likely to get caught. Like, you all have probably met people that have gone to MIT, like, a few times, right? Like, anyways, you can tell. And good for them. Okay, so to motivate our technique for Merkle trees, blah, blah, blah. There's two reasons to treat heaps. First, it solves the problem we're having, and second, I don't know if you learned it in data structure, so I'm going to teach it to you. Versus other graph representations, heaps are really good at doing something that I always want to teach you, which is that the structure of the graph does not have to match the structure of the implementation. We can implement a graph without just creating a set of nodes and edges. And this is cool, and this is a technique that will come in handy, I think, a lot. I can actually give a very specific example of when this came in handy for me. Some of you took CS 151 and implemented the Enigma assignment, right? The original version of the Enigma assignment, some of you will remember this, on the very first milestone, what you're supposed to do is you press a key on your keyboard and you click it. The original assignment instructions recommend maintaining a dictionary of every key on your keyboard and tracking true, false, whether that key has been depressed or not. That is, in fact, one way to represent which key has been depressed. The way I solved this is I used a different data structure, and the data structure I used was a variable. That variable was called letter, and it stored the letter that was currently being pressed or none. So I actually used the option type. Once you recognize what information you're storing, which is that if you have a dictionary that has at most one true in it at any time, you can just store an option of that type and then store whether a letter is pressed or not, right? So it is true that abstractly, I am storing the entire hash table representation of all English, of all Latin characters. So the characters used in English, but they're all Latin characters. But I only incur the information cost of storing a single letter option, right? And so that was a sort of design decision I was able to recognize on Enigma that I think correspondingly made Enigma easier for my section and so on, right? And then I hope you can all make these recognitions as well. I mentioned the diff assignment, and I was using a vector to store line numbers, and it turns out you don't have to do that at all. The information was completely redundant. And so sometimes the correct way to store a graph is to not store it, right? But sometimes the correct way to store a graph is a way other than that which you would most naturally expect to store it. And so we're going to do that with heaps. Why are heaps called priority queues? Well, they have some sort of invariant, or they have some sort of sorted relation over them. Heaps are nonlinear in that one node may have two child nodes, but they can be linearized. In this way, they are similar to, for example, JSON, which can be serialized or deserialized, right? So they are a nonlinear but linearizable data structure. Oh no, I have a loose asterisk. Okay. They kind of sort data, but they don't really sort data. What they do is they always give you the minimum or maximum. So the data is not in order, but if you take the data out of it, it will come out in order. So the heap will always have some sort of minimal or maximal value within the collection in its initial position or root. Let me just draw a heap on the board. So, this thing is not in order, but every parent is smaller than both of its children. So this is really useful to you if you are a young person, because if you are organized in a heap, then you are always larger than your parents and can overpower them with your numerical superiority, right? So this is really popular with the kids. I like to teach this at daycares. So this is an example of a heap data structure. Is this a complete tree? Is this a perfect tree? Is this a tree? If this is an n-ary tree, what is n? Okay. And in fact, it is actually only complete if n is 2, right? Because it could be the case that I put 3.5 here. No one was preventing me from doing that. Okay. So we're going to start with, we're just going to step through an example of heaps and how they work. And I'm stressing myself out because I don't know what time it is. Okay, cool. Do you all have like secret techniques to prevent your voice from perishing? You just suffer through it? Okay, all right. Heaps are usually based on binary trees, so we're going to do that. We're going to put the heaps on the right side of your screen. There's not currently anything there. Okay, here's an example. We're going to imagine inserting 128, great number, nice round number, also known as OX80. Remember? Throwback. Yeah. Who loves hexadecimal? Can I get a whoop whoop for the hexadecimal representation of the integers?
Whoop, whoop.
That did not seem like I could get a whoop whoop for that. Is it the whoops you don't like, or is it the hexadecimal representation? Okay, so when I have one value and I throw my value in my heap, well, it's the maximum value or the minimum value or whatever. So it's at the root of the heap, right? What happens when I add another value? Well, let's imagine we want to put 64 in here. So I want to insert another value. I'm going to insert an unpopulated node. And I have to insert that unpopulated node somewhere, and I have to insert it somewhere so that the shape of the tree is still going to be complete. In this case, I do not think it is perfect. I think it is only complete because I do not have a filled row 2 in my binary tree, but this node can be leftmost. So we're going to take the binary tree, and we're going to take the first child of 128. I also have capital I's on insert here, and I was pretty sure I fixed all of those. it is a real mystery who makes my slides. Sometimes I see things in here, I was like, that doesn't seem like me, right? Like where is it? Like this one? What's going on there? Okay. So, how are we doing this? We're going to put a 64 in the available node. 64 is less than 128, so it is completely reasonable for 64 to be lower than 128 in the tree if this is a max tree, right? So this is a tree that parents favor because parents want to have numerical superiority to their children, so they can outvote them and decide to go to Chili's instead of Applebee's, right? We've all been there. Is there a Chili's in Salem? I know there's an Applebee's here. You all are eating good in the neighborhood, right? There's one, okay. I do love Chili's. Not really sure about Applebee's, other than the flavor blasted steaks, which they discontinued. Okay, so 64 is less than or equal to 128, and that is A-OK. Do not read this. Someone took this seriously last year. I am telling lies. A-OK is not short for Ada, Oklahoma. Okay, we're going to insert an additional value. These values, represent how important something is to do, right? So for example, in my life, it is usually relatively unimportant to take out the recycles, and it is often highly important that I have a cookie, because if I don't have the cookie, my blood sugar isn't high enough to take out the recycles, so I have to have the cookie first, right? But then after you've had 7 cookies, then it is more important to take out the recycles because you have high enough blood sugar that it's no longer important to have more cookies, right? So things have changing priority. So we're going to imagine that 192, this is going to be cookie priority, 128 is take out the recycles priority, and 64 is stub my toe priority, very low priority, right? So to insert a value, I'm going to insert an unpopulated node that would make a complete tree of the appropriate size. By the way, that is how we have inserted every node. That's how I inserted the last node. That is an invariant. Okay, so I'm populating out the next level, and I'm going to put a child node there. We're just going to slap 192 in there. That's cookie priority. And this is a huge disaster, because if I attempt to take out the recycles before having my cookie, my blood sugar will dip too low while I take the 6 flights of stairs down to my recycling bin, and I will be unable to scale the 6 stairs back up to my apartment, becoming trapped in the recycling room forever, where I will slowly either rot or go insane, right? And so that is bad. So how are we going to solve this problem? Well, somehow we need to make sure that whatever is going on here, parents are always larger than their children and enjoy numerical superiority. This is called the heapify operation. And with smaller trees, it's quite simple. We're going to loop over it, but in this case, there's not going to be a loop. If, when you insert something, it is larger than its parent, all you do is you swap it with its parent, and then you check to see if it's at its new position, it's still larger than its parent. In this case, our new position doesn't have a parent, so we don't have to do anything. So all we're going to do is we're going to take 192 and 128, and we're going to do a switcheroo. We're going to do the back and forth. And when we're done, 192 will be ahead of 128 and 64, and we'll be able to eat our cookie both before stubbing our toe and taking out the recycles. Okay? You all recycle? For a while, the recycling bins on campus were maintained by Climate Action Alliance. Is that still true? I see these recycling bins on campus, and I was like, is this just going to the landfill? That's what I wonder. So one of you should look into that and get back to me. Okay. Now we're going to insert 96. I'm going to once again repeat the process I have done many times, where I'm going to locate where the next node would be if I had a tree that was one size larger, but still complete. In this case, it will be the leftmost node, but it doesn't really matter which side is on while we're filling it out, of the leftmost child of the root. So that is 64's left child. I'm going to insert a 96 there, and I think what is something that is intermediate in importance between stubbing your toe and taking out the recycles? I don't know. Singing a sea shanty, right? So you don't have to do that to live, but it's more fun than stubbing your toe. Okay, so we're gonna sing a sea shanty. Do I know any sea shanties? I also don't know how to sing, so it's irrelevant. Okay, we're gonna put a 96 in here somewhere. So how are we gonna do that? We're going to put the 96 inside the new node, and then we are going to heapify. So how are we going to do that? 96 is greater than 64, and it is below it. So we're going to swap the 96 and the 64, but we are not going to swap the 96 and the 192 because the cookie is still more important than singing the sea shanty. Okay, so that's how we decide how many ways we swap it up. Now, very vastful? Surely that's meant to be wasteful. What would vastful even mean? Because like vast sort of already means a lot of, and then full also means a lot of. I guess that's like bountiful. Okay, so we can just implement this all like so, right? But what we probably want to do is we probably want to put this thing in an array somehow so we can get access to these performance benefits instead of dealing with these performance benefits down here, right? We are always inserting new elements into the next available position in our tree, which means we can just treat that as being the next position in an array somehow. And if we're doing that, then all you have to do is stack push. Is it vector push? It's vector push, right? What? Print? Yeah. Just push. And I think those go on the end. Okay. So we're just going to vector push. So it is a simple enough matter to say, hey, you know what? The heap isn't going to be some big thing. We're not going to make some struct of it, right? We're not going to come over here and do all of this stuff like we did with the linked data structure. Instead, we're just going to directly use a vector, and we're just going to say the vector is a heap. This is a little bit sloppy. We should probably do capital H and like a T or something. Like, I don't know. But like just for sake of example, we're going to say, we're going to do this. A heap of something is just a vector of something. But we're going to have some additional infrastructure around it. And I also wrote 0 3 ways here. Isn't that fun? So this is text 0. This is code 0. And this is LaTeX 0. Yes? So none of those things are equal to each other. So we can imagine this as existing in some vector in practice. And the vector positions represent the order in which things are added. So 192 is not the first thing we put in, but it occupies the position of the first thing we put in. And should I be saying first? I'm going to say 0th, or initial, right? 96 is occupying the next location, 128 the next location, and 64 the next location. So we're just sort of slaloming down the mountain of the heap. If we're going to insert 160, and this is intermediate in priority between eating the cookie and taking out the recycles. So this is probably like putting the cookie box in the recycles before you take it out or something. Like important to do that before, but you can't do it until after you eat the cookie. I had a delicious pumpkin loaf today. It was great. Would recommend. So we're going to take recycling the cookie container, or putting the cookie container in the recycles, and we're going to put it inside our tree somewhere. So where's it going to go? We're necessarily going to create the next available position in the tree representation, and we're also going to create the next available position in the array representation. We're going to insert the 160 at that location, and then we're going to take note. We're going to notice that this 160 has numerical superiority to its ancestors, which is unnatural because you should always respect your elders. So we're going to rearrange this so that the elders are respected. How are we going to do this? Well, we're going to perform a swap. What swap are we going to perform? We are going to move the 96 and 160, and we're going to interchange their positions. I tried to represent this with an orange arrow here. I don't know how clear that is, right? But we take 160 and 96, and then we change it to 160 and 96. Now, the way that you determine in the array where you swap to is kind of non-trivial, because you have to understand in the graph representation, where you have sort of nodes and edges, where the ancestor is, right? So somehow you have to know where to swap for, and you can't accidentally swap. For example, 160 with 64, even though 160 is larger than 64, that would not cause you to end up having a satisfying heap, because there'd still be a 160 here, there'd still be a 96 here, and you would still be in big trouble, right? So somehow, when you're performing these swaps in the vector, you have to keep track of who you are swapping with. Okay, so what's going on here with the indices? We can think of this relatively straightforwardly by saying, hey, look, 160 is inserted as the element at 0 index location 4. Why am I saying 0 index? Because since I'm giving something by an index, I have to say what it's indexed by, right? So if I'm 0 indexing, 160 is at index 4. Okay. I'm going to change it or swap it or test it against its ancestor is at 0 indexed position 1. If I were to implement this algorithm, it requires some certain amount of thinking to understand where the ancestor node is for any newly inserted node. So how am I going to figure this out? Well, I'm going to use a little trick. I'm going to cheat. First of all, I know the answer, and second of all, I know how to do division. So I'm going to do both of those things at the same time. Now, 2 and 3 both have an ancestor of 1, and then 4 and 5 have an ancestor of 2. So what does this mean? Well, this is very close to integer division by 2. But we are off by a little bit. Specifically, we are off by 1. So how do we solve this problem? Well, we switch to using a 1-indexed array. Now, okay, big hater, which is known to be enrolled in computer science of this program. We have many haters all around us that hate on specifically the R project for statistical computing for being 1-indexed, which many haters falsely claim means it's not like real computer science or something. I am showing you, I believe, one of the only examples I am aware of in all of algorithm design where it actually matters numerically what your index is, and you want to 1-index this thing. So actually, 0 indexing is weird and cringe, even though I like it better now. Okay, so anyways, next time someone is complaining about 0 and 1 indexing, ask them how heapify works, and then you will have defeated your adversary, okay? Unless you're in support of 0 indexing, then do something else. Okay, so what do we have here? 2 and 3 divided by 2 are both 1. 4 and 5 divided by 4 or by 2 are both 2. So the way you can find out where your ancestor is in a vector is you simply divide your index by 2, and that tells you the location of your ancestor. That's awesome. Division is easy. Remember when I made you implement big int, how easy division was? Okay, so it's pretty hard, right? But there's things that are harder. Okay, we're going to insert 224. This is higher priority than eating a cookie, right? And there's not a lot of things that are higher priority than eating a cookie. So what must this be? This has to be your electrolyte beverage, right? Because the only thing more important than maintaining your blood sugar is maintaining your electrolytes, right? So this is probably maybe like a little sip of Gatorade Zero. Do any of you get into those Noon tablets? The little ones that fizz up? Do you all maintain your electrolytes properly? Okay, well, make sure you're taking good care of yourself. Do you all sleep 8 hours a night? Okay. I am not your wellness instructor. So, okay, we're going to insert 224 in position 6, and this is the importance of having well-balanced electrolytes in your diet, which help you maintain a healthy blood pressure. Sometimes when I'm feeling fatigued, I'm actually just low on sodium or magnesium, right? We've all been there. So we're going to insert 224 in position 6. And then what are we going to do? Well, we're going to realize that in order to maintain the property where the maximum value is at the root of the heap, and parents always enjoy numerical superiority to their children, we're going to have to make sure that we don't have to perform any swaps in order for that to be true. So we have to figure out what 224's parent is. But we can do this with the operation of divide by 2. 6 divided by 2 is 3. So this right here, 128, must be the parent of 224. So we're going to check that. We are going to see that 128 is less than 224. We are going to execute a swap. We are going to move the 224 to where the 128 is, and vice versa. And then we are going to check, once again, we are going to check 3's parent. What is 3 divided by 2? 3 divided by 2 is 1 when we are using integer division and we truncate. So then we are going to compare 224 to 192. We're going to see we must execute an additional swap. And so we're going to execute that swap. At that point in time, 224 has no remaining parents, so we don't have to do any other checks. And separately, for those of you following along at home, you can note that 92 is still 128's parent, so we're still maintaining the property of parental numerical superiority over children. And this is what it looks like when you're at the end. We have sort of a chain down here to where we inserted 224. We swap 192 and 128 both down, and this other side is unaltered. There's nothing wrong with it at all. And so this is what the heap looks like in the two different views. But note, the only thing we have to do to maintain this is we only need a single vector. We do not have to keep track of any edges at all. These edges emerge naturally from the heap property, and all we have to do to find what something's parent is divide by 2. And that is cool as heck, is the technical term for how cool that is. Merkle trees. Does anyone want to ask me any questions about heap before we go on? Okay. I kind of want to make you implement a heap, but it seems tedious. And so I don't know if it's more useful to have you do that than something else. So that's one of the things I'm struggling with right now. I usually enjoy the process of implementing heaps because you get to do this sort of mathematical trick. And it's very rewarding when you get the indexes to work correctly and the heap just heaps. It's also a relatively fast way to sort lists if you're into that. Anyways, Merkle trees. So we introduced the heap to give sort of an algorithmic reason because, we're computer scientists. We sort of can't help it. We love sorting integers, right? And the heap is really good at sorting integers, right? It sorts those integers so well, right? We put a bunch of integers in a heap and then we take them all out and they're in order. Oh, that's so exciting, right? Maybe there's something even more exciting than that, and that's the use of the Merkle tree. The Merkle tree has the same feature as a heap that enables it to be stored in a linear data structure, which is that the Merkle tree is always complete, and sometimes it's perfect, right? It's going to be binary, it's going to be complete, because we're always just going to be adding new hashes at the end. Okay, so how are we going to deal with that? All we have to do is we have to take the same sort of linearization scheme that we applied to the heap, and we can apply it to the Merkle tree, but we have to deal with one wrinkle, which is that Merkle trees contain hashes and they also contain data types. So we have to deal with that somehow as an implementation decision. So I've created a series of things that I think I would plausibly do to alter a code base. For example, sometimes, and I think you can't do this in Rust, right? Nvim circ main. So I think, what am I doing? Insert, okay. I think this is against the law. Let x equal 0. Right, so, is that allowed? Okay, that is allowed. Is that not allowed in Python? Oh no, it's plus plus. Okay, wait, hold on. So I always want to do nvim circ main. Okay. There is this programming language that exists that has the double plus operator. There we go. Cargo run. And in fact, the plus plus operator is so common that Rust can tell you what you mean, right? Which is really cool. And I think, there's not plus plus in Python, is there? Wait, what? Okay, so you can just put as many pluses before something as you want and it doesn't change the value? Okay. That's crazy. Do you like that? I kind of want to start writing my numbers like that now. Not really sure where I was going with this. Anyways, something I'm often changing about my code is how I'm writing my increments. So there's the sort of assignment update, And then you can separately do assignment with a numerical change, right? So this is an example that something CD could change in a code base. Then there's my alter ego, Professor C. Sometimes I change my if trues to if ones. Why do I do that? Well, here's a fun fact. Do I have Node? So if I start typing here, and I want to say true, do I use a capital T or a lowercase t? This is a programming language, right? Do I use capital T or lowercase t? I don't know, but if I say if one, nope. Okay, I can't do that. Okay, that's allowed. That just auto-completed? I'm pretty sure that auto-completed, and I don't know why. That's extremely scary. I was able to just write if one without knowing if I have to write true or false to get a Boolean, right? I'm pretty sure in this language true is banned and true is allowed. But I sort of just gave up using Booleans because that's a lot of work, and I just use 0 and 1 for everything now. People love this. People love looking at my code and saying, oh, that makes so much sense. So we can imagine I changed if true to if one, right? Sometimes my third alter ego, Calvin, names every single variable I. Have you seen me do this? I just call everything I. And that's not what you're supposed to do. Sometimes you have values, right? And you should call them values. My values are 0, right? And then, maybe there's another change to this code base and someone comes along and sees, wait a minute. I said x equals x plus 1 because I was confused that there was a variable floating around named I, that it wasn't, I think, the one that I wanted to work with, but it actually turns out I wanted to be working with I the whole time. And then Professor C noticed that, hey, that I value is actually what I wanted to use, or this x value, blah, blah, blah. Okay, then we change a bunch of things around, right? So here's some plausible minor changes to a code base, right? You can imagine these are all single line changes, for example. So wait a minute. We can actually do this. Okay, so running example, cargo run. This is not possible. But I can make a copy of that. Sort hold. No. Main. There we go. No, what? Oh, I copied it to local old. Okay. So this is an example of what the diff could look like, and it's quite similar to something I just did, right? So we can create those examples, and we can see them, and then we can change our code correspondingly, right? So I can store all of this in an array somehow. Does that seem too hard? Well, minimally, if we're looking at this, we can say that this is an array of 3 strings, right? And so we can have an array of 3 strings, and we have a vector of an array of 3 strings. Obviously, you can also put this in JSON, right? And you can say this is an object with keys user before and after, and then you have a list of the dictionaries, right? So in a complete binary tree, we can take this, and I have 6 things here. We can say we need to put this in some sort of hash tree somehow. And in order to have the type of tree we want that can be linearized, we have to have a complete tree. So how are we going to put this inside our complete tree and then start hashing things up? So what we're going to do is we're going to take our 6 entries, and we're going to recognize that the sizes of the last row of a tree are always some power of 2. And 6 is not some power of 2, so we're going to need part of a row of size 8 and part of a row of size 4 in order to make this work. How are we going to do that? Well, let's just sketch out the row of size 4. We need additional things on here. So what are we going to do? We can just add children to it until we have enough. If we add 2 children to one of the nodes, that gets us up to 5 positions. This is still not enough. So we're going to add 2 children to another one of the nodes, and this gives us 6 leaves. 1, 2, 3, 4, 5, 6. And how is leaves spelled? Leafves, right? So we remember leaves. Okay. And then all we have to do from here is however we are storing those diffs, and perhaps this is one way to store a diff, right? We can do it like this, or perhaps you can do it however you want. We're going to take those diffs and we're going to hash them so we know that the difference has integrity, that no one tampered with the difference, that we are going to not make some unintended change to our source code. So I did that as follows. I took my 6 changes and I just wrote them linearly across the last root nodes. Now, there's something that's a little bit weird here. It is ambiguous whether these nodes come before or after these nodes. How did I decide to do it here? Well, I actually just didn't want arrows crossing each other. So that was the design decision made here. This is just a visualization decision. Then what are we going to do? Once I have those commits, which here I'm just representing by their identifier, I'm going to take the vector of commits and I'm going to hash each of the commits, and I'm going to store them in the leafs of my tree. So I'm just using H to denote the hash there. And then I can sort of hash all the way up to the top level. Now, this looks a little bit wonky. I understand this because it looks like there's 3 nodes in this level. Check the indices, right? I don't know how to visualize this the best way, so this is what I did. 1 has 2 children, 2 has 2 children, 3 has 2 children, 4 has 2 children, 5 has 2 children. Collectively, this stores all of the hashes. We unbox the children, or whatever you want to do, right? And then we hash them up to the root, whereas in the root here, which I'm still regarding as at index 1, right? And why did I use hexadecimal? Because I ran out of numbers, so this is A. I'm hashing sort of all the way up to the root, but this hash means that if there's any alteration to a single one of these commits, it will change all the way up. And furthermore, I will be able to determine which commit was altered by finding the first place that the hash differs. So that's how you can use a Merkle tree to store diffs in Git. The root of the tree contains a hash known as the Merkle root, and it is sufficient to check only this hash to know you have an untampered repository. And I think I've taught you what Merkle trees is. Does that sound right? Okay. I do want to do a quiz for understanding. Why do I need a Merkle tree? You already answered today. Oh, wait, okay, you haven't answered yet today.
Well, it ensures everything was done correctly and you know exactly what's in there, because hashes are very cool.
Okay. So if the hash doesn't agree, I shouldn't install the operating system. Okay. Isn't all of this hashing kind of expensive? What's the alternative? Do you have something? Yeah, okay. Yeah, and if we don't do any hashes at all, then our computer explodes, and if we do too many hashes, then we never get to use our computer. And so this is a balanced approach to how much hashing we do. What's the thing I'm hashing again? Uh-oh, we're running out of people who are willing to talk. Okay, the thing I'm hashing, I'll tell you. I'm going to let you off easy this time. You're hashing the changes, right? So in the case of version control, right, it's these diffs or something equivalent to these diffs. And in the case of Bitcoin, which is the other thing I know that uses Merkle trees, it's someone spending a Bitcoin, right? So you just hash every time the system you're managing changes. So some change occurs to the system, you hash it, you rebuild the tree, you send the Merkle root across the network, and everyone can verify that we all agree on everything that happened. Okay, I think that's all we have for Merkle tree. Does anyone have any questions? I could talk, but I don't want to. Does anyone want to ask me anything about least common subsequence? Wait, was there not a lab? Oh yeah, oh, how was Jimmy talk? What'd Jimmy talk about?
Memory.
That's a broad topic. Okay. Did you learn anything we should incorporate? Did Jimmy do arenas? Okay. Okay, that's right. So you didn't have a lab because you had Jimmy talk. I'm going to ask you to do diff. And I think I'll ask you to do diff and heap, I guess. I think that's what makes the most sense. Do y'all feel like you could implement a heap in, like, not some large number of hours, right? I think that's like a couple hour thing, like that's a reasonable sized homework. Diff is a reasonable sized homework. Okay. Then I'll introduce the VCS next time, and then I owe you one talk on either computer organization or architecture, and I couldn't fit it in earlier because we had to build everything up. So that will be the last week of class, and then the VCS will be due whenever the final is. When is the final in this class? Willamette, academic, wait. How do you find out when finals are? Willamette, finals schedule? Is it? It's fall, right? It's 1:10. So have a version control system implemented by this day, and I will go live on either Discord or Twitch to answer questions at that time. Because you own those 3 hours of my time, so you can ask me questions then. And then at 5 o'clock, make sure that you have some commit to your version control registry. And I'll come up with some write-up that says how you're supposed to submit that. Do you want partners or individual final project? And if you do partners, you're required to actually both contribute to it. So like that is, it's not less work or more work, it's just different work.
How many people?
2.
2.
I think it has to be 2. There's not quite enough stuff for it to be 3 people.
What if we do with partners if we want, or individuals if we want?
So, historically, I would have done that. I'm anxious now because I think to get this program the type of accreditation it wants, I need to have projects that are specifically partner and projects that are specifically individual, so I have to force one of them in both cases. My inclination is the way to do that is have a mandatory partner project in this class and then make the advanced class have a mandatory individual assignment, but I'm not sure that actually makes more sense. Think about it. I might compel and even assign partners and just like emotionally prepare yourself to deal with that. And I won't do that if it's going to be a disaster, which it could be at high probability. Okay, I think that's all I have for today. If no one has any questions on LCS, you can leave if you're quiet. Shh, there's other classes going on. Come talk to me right now if you have any advising questions. I think I got back to everyone. I don't know if that's true. Oh, my voice hurts.